And for some reason we have an advertisement I don't want to see. And we even have Fred here. Or Freddie, or whichever you go by. I don't remember. Okay. All right. Let's get the slideshow set up from the current slide. And before we begin, let me go over just the only, I guess, sort of major announcement I know about. I'm sort of behind on emails because I had a stack of papers that big to grade over the weekend. I got most of them graded, but not all, so I haven't checked up on emails much at all. I just am ending the first mini-term class, and it was a lab class with lots of people turning in late labs and making up tests and that kind of stuff. Okay. All right, over near the plug today. Elise, right?
Yes, sir.
Okay. I thought it was because you wanted to be near me, but no, it's the plug. Yes, okay. Yeah, right. Okay, wiped it off. Okay, never mind. Okay. All right. Yes, sir.
Before you get started, that was a definition on section 3.3, page 181, definition of increase and decrease. Can you take a look at that definition?
Okay.
Of course, you might have said something about it.
Yeah, now, in my memory, the slides was wrong, but the book was right, I think. Which one is it that you're... Oh, no. It's the top definition at the top of the page. Yeah, and I mentioned that. The last line, a function f is decreasing on an interval when for any two numbers x1 and x2, and the interval x1 less than x2 implies that f of x1, it says less than, which is the same as increasing, and it can't be. It's greater than. Yeah. And that's 11th edition, and they still haven't found the error. It's on the slide set. It's on here. I had made it in an earlier, noted of it in an earlier class. I hope I said something last time. Okay. Now, what I was going to mention now, though, is, as I said, first mini-term class is drawing to a close tomorrow, and Wednesday starts the second mini-term. So sometime around midnight tomorrow night, that's the middle of the term. Sometime after the middle of the term, they usually ask for midterm progress reports. And I think all of you are in great shape, as far as I can tell, except for 2 people have not turned in the first test. And neither of those has turned in a research paper. We've already got 2 people that have turned in the second test. So now I'm preaching to the choir here. All of you have turned in something and have good scores from it. So y'all are in good shape. It's 2 people who are not here need to get something to me soon. Doesn't have to be today. Doesn't even have to be tomorrow. My guess is they give us till probably about the end of this week. But if I have not received something by the end of the week and they require us to turn in a midterm progress report, it's going in that those 2 people have F's at midterm, which I don't think is realistic, but it's all I've got. Okay, so please, folks, get in either your research paper or your first test or your second test or all 3 or any combination of those as soon as you can. All right, now that leads to something else. I said in by Friday. Getting it to me on Friday isn't going to do any good because this Friday I've got a meeting down in Mobile that starts at noon. So that means I'm going to have to leave home right around 7 in the morning to be sure I get in Mobile and find the place by noon. They say it's a 4 to 5 hour trip, so I want to allow at least 5 hours for travel. I probably will have to stop at least once. So I will be leaving home at 7 and getting back around 8. So it's a 3-hour meeting, and so if it ends at 3, I'll leave there 4 to 5 hours, be 7 to 8 o'clock. And I may have, definitely going to have to stop a time or two there. So I will not be in the office at all on Friday. So that means I have to have it in by sooner. Okay, Devin's here. All right. Okay. And what I was just saying to the others, midterm is sometime between Tuesday and Wednesday, probably midnight on Tuesday night. And usually right after midterm, they ask for midterm progress reports, which we have to report anyone with D's or F's at midterm. So and again, I'm preaching to the choir here. Y'all have all turned in things. But I haven't got everything on Blackboard yet. I was grading like crazy all weekend, but didn't get everything done. Got your papers done, but I didn't get it on Blackboard. So I just got another one in this morning that's not grading. But I need to have at least a test or research paper or something in by probably the end of this week. However, I'm not going to be on campus on Friday because I've got articulation meeting down in Mobile that's only goes from 12 to 3, but that's a 4 to 5 hour drive down there and a 4 to 5 hour drive back. So I will not be on either campus at all this coming Friday. Now, next Friday, I've got a doctor's eye appointment right across the road here at the UAB West at their eye center, and I will be, that's an 8:15 appointment. So I'm hoping to be through with that by 9:15. We'll probably be heading to Birmingham after that. So just to let you know in the future, won't be on campus. I'll be on this campus right at 8 o'clock, but then I'll be heading over there for my appointment at 8:15. All right. Any questions before we get started today? Okay. And like I was saying also, I got this class graded except the paper that came in this morning. But I don't have them in Blackboard yet. I'm sorry? The paper, the research paper, it was due any time in the term you want it to come in. Starting now, the first class day of March, you only get 2 bonus points for coming in the March. And 1 in April and 0. And I think it's just the first 2 weeks in April. And then after that, it's just your score. Okay. Any questions? Any other questions? All right. And Bill had a question. Hope I said this last week, but if I missed it, on the top of page 181, the first definition listed on it's the definition listed on the page. That last line, the last inequality is facing the wrong direction. That should implies that f of x1 is greater than f of x2. That's for a function to be decreasing. The f of x of this function thing has to be greater than f of something to its right. So that's a greater than sign. All right. Now, if my mark is right, we got started on this problem but didn't get it finished. Is that correct? Or did we even get started on it? Example 1. What's that? Okay, I worked it out, but we didn't see what they did. That's where it was. Okay, I knew I had it marked further down. Okay, find the open intervals on which f of x is equal to x cubed minus 3 halves x squared is increasing or decreasing. Okay? What's our first step? Take a derivative. Okay, we did that. And hopefully we got also, well, no, they just wrote it down yet. Good for them. Okay, but when they took their derivative, they got, I hope, the same thing we did. 3x squared minus 3x. I believe that was correct. Okay, now, I don't know if they're going to do it the same way we did. What did we do next? Anyone recall? Here's Josh. Okay. while y'all are pondering that question, let me say again what I had announced earlier, because Josh wasn't in here. We're rapidly approaching midterm, which I think will be midnight Tuesday night, okay? It's midterm. And sometime after midterm, they usually ask for a midterm progress report in which we have to respond with anyone who has a D or an F at midterm. So if you, in any of your classes, or if you know of anyone who hasn't turned in some work at midterm, in other words, you don't have a grade, then that person's probably going to get a D or an F reported on midterm. Doesn't really mean a lot, except you may start getting bugged. Well, do you need tutoring? Do you need counseling? Do you need, various things? So I would be great if myself or any other instructor would have work turned in before the end of the week. That goes along with the fact that I'm not going to be on either campus on Friday. I'm going to be in Mobile at an articulation meeting. All right, so here we have f prime is equal to that. What's the next thing we did? Set it equal to 0. Hey, we weren't asking for critical values here, were we? No. So why would we set this equal to 0? Okay, that will help us define the interval, because if it's increasing somewhere, and by the way, what kind of function is this? Good old P function. What is that? Polynomial function. What two things that are true about all polynomial functions? Smooth and continuous. So therefore, there's not going to be any places where the first derivative doesn't exist. And no gaps, no breaks in the function. So if we find that where f is 0, it's either going to be increasing coming up to f equals 0, first derivative equals 0, or it's going to be decreasing coming down to that. And on the other side, it's going, in other words, it's going one direction before and after each 0. Now, if there were places where it weren't defined, you'd have to investigate that too. So if we find the zeros here, then that sets the interval, like Dawson said. And what do we, okay, so let's see what they do. They did the same thing. To determine the critical numbers, I like to call them critical values. That's all I've always called them. They call them critical numbers. We set that equal to 0. We found out they were x equals 0 or x equal 1. Now, was 3 equals 0 a critical value? They did x equals 0 and x minus 1 equals 0. That's x equal 1. Is 3 equals 0? No, it's not true, is it? 3 can't be 0. Okay, so that's not a value at all. Don't even go there. Okay, I've had students give me that as a critical value. No, 3 is not 0, so that doesn't count. Okay, so x equals 0 and x equal 1 are your two critical numbers. So you know one interval, we don't know if it's increasing or decreasing, it's going to be to the left of 0, one between 0 and 1, and then another possible one between 1 and infinity from there on. It can't turn around again. If it's increasing up, well, let's say, take this one. If it's 0 there, it's either going to be increasing or decreasing after that, because it can't turn around either way, because it's a smooth continuous function. It would have had another critical number after that. It doesn't. So therefore, it's going to be strictly increasing or decreasing before, between, and after these values. Because there are no points from which f prime does not exist, you can conclude that x equals 0, x equal 1, the only critical numbers. Good. And the table summarizes the testing. And that's what we do next. We pick a point to the left of 0, between 0 and 1, and to the right of 1. And that's what their little table shows. They picked -1 to the left, found out it was positive. F prime was positive there, so therefore F was increasing. This is an F prime. F was increasing, okay? And then between 0 and 1, they picked 1/2. I think we did too. We found out it was negative there. So between 0 and 1, the function has to be decreasing. And then we picked another value greater than 1. They picked 2. I think that's where we picked as well. And found found out that was positive again, so again it's increasing. So increasing from negative infinity to from negative infinity to 0, from decreasing from 0 to 1, and increasing from 1 to infinity. Now again, when you label these, I like writing them like this. It's a little bit longer than interval notation, but it's a lot, to me, is perfectly clear. If you're doing interval notation, notice they don't include an equal sign here. So don't make them brackets ever. When they're talking about intervals like this, make them open intervals, okay? Not that it'll take off any, but that's typically, because we don't know where it's equal to 0. Is it increasing or decreasing there? Well, it's neither one, but that's only a single point, so don't include it. Okay. So here we have a picture of it by the theorem. F is increasing on interval from negative infinity to 0. Notice how they put a parenthesis there. And increasing again from 1 to infinity. Okay. Now remember, your intervals are always defined by your domain, the horizontal axis here. From minus infinity to 0, increasing, from 0 to 1, decreasing, and from 1 to positive infinity. That positive infinity, it doesn't matter what it's doing up there, it's going to, x is going to positive infinity. Okay? Increasing again. Make sense? The figure makes perfect sense. Okay. Any questions on that? All right. Now, example 1 gave you one instance of how to find intervals on which a function is increasing or decreasing. The guidelines below summarize those steps that followed in that example. So here we're going to go through the steps again. If f is a continuous function on this interval from a to b. Now that doesn't necessarily mean it's smooth, but it's just continuous. It doesn't have any breaks, gaps, holes, or things like that. To find the open intervals on which f is increasing or decreasing, use the following steps. First, locate the critical numbers. And again, remind me what the critical numbers are. Where what? Where what?
X is equal to 0.
Not quite.
Intercepts the x-axis.
What?
It intercepts the x-axis.
No. Okay, that's not a critical value. That is an x-intercept. That's a 0 for the function. What is a critical number? It's something's equal to 0, but it's not x.
The slope of the tangent line.
It's what?
The slope of the tangent line.
Okay.
Is it the slope of the tangent line that's equal to 0?
Yeah, the slope of the tangent line is equal to 0. And how do we get that? Yeah, that's what we're talking about. Yeah. How do we get it? Take a derivative and set that equal to 0. That's what's equal to 0, the first derivative. Or where the first derivative doesn't exist. That would account for any continuous values that may not be smooth. Points, cusp, things like that. The first derivative will not exist at those points. So we have to also consider those. So the critical numbers, again, this is a review, where the first derivative is equal to 0 or the first derivative doesn't exist. And that's all determined by your first derivative. Okay, so first thing, take a derivative, first answer, okay? Then the critical numbers are where that's either equal to 0 or doesn't exist. Use those numbers to determine your test intervals. Test something to the left, something in between, and something to the right of every pair of those, okay? Determine the sign of f prime, first derivative, as one test value at each of the intervals. You only need one, okay? Because in between the intervals, you can't have any other places where the first derivative is 0 or doesn't exist, because you found them all when you did that first step, okay? So it's got to be either strictly increasing or decreasing in between any of those critical values. And then we determine whether it's increasing or decreasing. Okay, you determine the sign of f prime at least one test value. What's true? What will then tell you whether it's increasing or decreasing?
Whether the derivative is positive or negative.
Yes, whether the first derivative is positive or negative. It's got to be one of the two. can't not exist, that would be a critical number. It can't be 0, that would be a critical number. Okay? It has to be where they have a value there, and they're either positive or negative. If they're positive, they're increasing, negative, decreasing. That is F prime, not F. F prime. But F is increasing or decreasing. Those guidelines are also valid when the interval A to B is replaced by minus infinity to B, A to positive infinity, or minus infinity to negative to positive infinity. It doesn't matter how big or small your interval is, that's true wherever. Okay. It's just what would be your test values. If this interval is A to B, don't pick a test value to the left of A or to the right of B. If that's limiting your interval, then pick your between those points in your test critical value. Sorry, can't talk. All right, now word I don't know if you've heard before: monotonic. A function is strictly monotonic. What does mono usually mean? One, okay? Now the little Planters peanut, he has that single lens. What's that called? A monocle. Mono, one lens. He does have two, okay? Okay, a monocle, monotonic. One direction, either up or down, okay? Function is strictly monotonic on an interval when it is either increasing on the entire interval or decreasing on the entire interval. For instance, the function f of x equal x cubed, strictly monotonic on the entire real number line because it's increasing everywhere. How do we know that? What would be your step? Take a derivative. What would that give you? 3x squared. 3x squared, when is that negative? 3 is positive, and x squared is always positive. It could be 0, but it can never be negative. So sure enough, increasing here, 0 right there, but that's okay, still increasing. Okay, so we usually don't count that place, but there's the only place that just for an instant at that value. This value over here is still increasing, this value right there is still increasing, so we say it's increasing on the entire number line. Okay. Monotonic, strictly monotonic function. Going in one direction only, never changing and going downhill. Or if it's going downhill, never changes uphill. Okay. Now, this function is not strictly monotonic. This is a piecewise defined function, and it's f of x is equal to minus x squared when x is between less than 0. Okay, that would be the parabola that went like this. However, it only goes up to there. It's constant at 0 from 0 to 1, and then it's x minus 1 squared, continuous, but not smooth. Now that looks pretty smooth, but it's not considered smooth because you have a change of your derivative. Well, not an abrupt change. I guess that would still be considered smooth. Okay? But piecewise defined function here is not increasing anywhere on that interval. Or decreasing either, but not increasing. So monotonic here, monotonic there, even though it's not increasing or decreasing, it's because it's only going one direction. So they're not all in the same direction. Okay. It's not strictly monotonic on the real number line. Does that make sense? Okay. Okay, I think, no, they didn't. All right, so we've already had our first derivative test, haven't we? No, this is something else. After you have determined the intervals on which a function is increasing or decreasing, it's not difficult to locate the relative extreme of the function, is it? Because we've already done that. That's where the first derivative is either 0 or not defined. Okay? That gives a hint. Okay? It doesn't tell us for sure, but it gives us the first step. For instance, in this one, okay? Remember this one? We had that at the very beginning. Okay? first thing we looked at, has a relative maximum at 0, 0, not an absolute maximum. Look over here, way past that here, okay? Relative minimum here, not an absolute minimum, way less than that down here, okay? Relative minima, extrema at those 2 points, okay? Now, before we took a test value here and found the first derivative positive, this is exactly what we've done before, so let's move on. Relative increasing immediate. Yeah. This is now talking about extrema. Now, first derivative positive here, meaning it's increasing. First derivative negative past 0. Just past 0 was negative. We found that out. That means this has to be a maximum. It can't be increasing coming up to 0 and decreasing after 0 and not be a maximum. So, whereas before, all that told us that it was a critical value, but it didn't tell us it was necessarily a max or min. Now we know it is. We know it's increasing before, decreasing after, has to be a max. Over here, decreasing before you got to x equal 1, increasing after that, that means that has to be a minimum. Okay? It makes sense on the graph. It makes sense everywhere. Even if these were places the first derivative doesn't exist, that statement is still true. Okay? If it's increasing on one side of a critical value, decreasing on the other side, it's going to have to be a maximum. Decreasing on the front side, increasing on the back. Let's go back here. This, well, not even that one. This one, increasing on this side, that is a critical value, right? First derivative is 0 there, but it's increasing on this side, so it's not a maximum or minimum. It's not an extreme value. It is a place that's a critical value, but it's not extreme. Increasing here, increasing afterwards, not an extreme value. And this would be too. There aren't any extreme values there. Obvious from the graph, but even if you didn't do the graph, you would have been able to tell increasing on one side, 0 on the other side, 0 on one side, increasing on the other side. Not a relative max or min. So that's what the first derivative test is telling you about your extreme values, okay? We already did first derivative test for increasing, decreasing. Now we put those together to give the first derivative test for extreme values. All right, similarly, f has a relative minimum at the point 1, negative 1/2, because f is decreasing immediately to the left of x equals 1, increasing immediately to the right. Therefore, it's got to be a minimum. Increasing coming in, decreasing coming in, increasing going out has to be a relative minimum. Okay? The next theorem makes that more explicit, so let's hear it. Let C be a critical number of the function. F is continuous. Now, f has to be continuous, not necessarily smooth, but continuous on open interval I that contains this value C, the critical value. If f is differentiable on the interval, except possibly at C, okay? Remember, that may be a place where that is your critical value because it's not defined, the first derivative is not defined there. It has to be defined everywhere else, otherwise that would be another critical value, okay? Somewhere else, okay? Then f of C is classified as follows. If f prime changes from negative to positive, the first derivative changes from negative to positive at C, then this has to be a relative minimum. If it changes from positive to negative at C, then f has to be a relative maximum. Okay? If f prime is positive on both sides or negative on both sides, then f of C is neither a relative minimum or a relative maximum. Okay? And that would be the case like we saw before. F prime is positive here, positive there, not a relative max or min. Negative here, negative there, not a relative maximum. Sure, the first derivative is 0 there. That's a critical value, but it doesn't mean it's a max or a min. Here, First derivative negative on one side, positive on the other side, minimum. Positive on this side, negative on that side, relative maximum. Make sense? First derivative test for your extrema. We were doing increasing, decreasing. We put that together for the extreme values. Does that make sense? All right. So here's example 2. Find the relative extrema of f of x is equal to 1/2 x minus sine x on the interval 0 to 2 pi. Relative extrema on that interval. What would we do first? Take a derivative. Oh, let me get my pen. I can't believe the first I've written. If I can get it to write. Okay. F prime of x then would be what? Would be what? Anybody? One half, perfect. Minus cosine x, perfect. What do we do at first derivative? Set it equal to 0, because that will find our critical values or numbers. Okay? Now, oh, put the equal, I didn't put the 0. Okay. How do we solve that?
Add the cosine over.
Okay, add cosine x to both sides. I think that's a great idea. Okay, so this will be result in, I'm going to switch sides now, cosine x is equal to 1/2. Now where between 0 and 2 pi is cosine equal to 1/2? Okay, pi thirds will certainly be one place, x equal pi thirds. Any others? Say again.
11 pi 6. Or would it be 7 pi thirds?
7 pi thirds is, huh?
7 pi over 6.
Okay, 7 pi over, okay,
7 pi over 6.
okay. 7,
5 pi over 3.
okay. All right. I think we're getting closer now. Okay, the last I heard was what?
11 pi over 6.
Okay. If that were pi 6, that would be it. But this is pi thirds, so this would be, say again?
So it has to be over 3, so 5 pi thirds.
5 pi thirds, just short of 2 pi. 2 pi would be 6/3 pi, and this is your, if you remember, we used to call those, goodness gracious, I'm going blank on the name, reference angle, okay? This would be the reference angle, and you need to get the other reference angle that is pi thirds on this interval here. For cosine, cosine is positive in the first quadrant, negative, negative, positive again in this quadrant. Pi thirds for the reference angle would be pi thirds short of 2 pi, which is 6/3 pi, so this would be 5/3 pi. Those are our two values. Oh, and by the way, this is a combination of a linear function and a trig function, sine or cosine trig function. Those are smooth and continuous everywhere. This was tangent, secant, any of those? Sine or cosine, perfectly fine. So these are going to be our only two critical values. No place where this first derivative is not defined. Okay? So, what are we going to have to do then to find the extrema?
Figure out where, so you have to plug it into the original function.
The what?
Plug the x into the original function.
Okay. X. Okay. You want to find
Or you
the.
just find, plug in a number that's less than the critical number. To the
Right. Okay. So let's set up our intervals. I think is what you're saying, right? First interval will be 0 to pi thirds. Next interval will be from pi thirds to 5 pi thirds, and the last interval will be from 5 pi thirds to 2 pi. Right? Okay. Now, where are you plugging in the thing? That's what I was trying to listen for.
So you take the critical number, and then to figure out if it's an extrema, you have to find a number to the left of it and a number to the right and see if it's what the sign is.
Okay, so you're going back the way we did it before. And that certainly works. You would find out what the value of the function, I thought that's what you were saying at first, is at the critical values. Okay, is that what you were saying? You could do that and then pick a number in this interval, that interval, that interval, and compare them to the critical values. That worked last time, and it'll still work. But if we're using the first derivative test, what is that? It saves us just a little bit of work. And I'm all in favor of that, okay? Because I'm lazy. How would this work? You still have to pick a value in the interval, but what you don't have to do is worry about what it is at the values. Maybe you are interested in that. If you're going to plot it, you're going to do it anyway. But here, all you have to do is get the first derivative here, so the value here, there, and there. That will tell you everything you need to know, right? So pick a value between 0 and pi thirds, and please pick one that's easy, okay? Frankly, I think 0 would be fine, but it's outside the interval, technically not included. So what would be a good value to do? Pi halves would be in this one, wouldn't it? So that will be a good one to do later. Pi fourths will certainly work. So let's do f prime at, I can't write, pi fourths, okay? That would be 1/2 minus, what's the cosine of pi fourths? Anybody know? Root 2 over 2, okay? Now, I don't care what value it is, really. Not too much. Not at all, really. I'm just interested in the SIGN sign of it, okay? And what is that? It basically comes down to which is greater, 1 or root 2? Root 2 is greater. So this has to be less than 0. Okay, got it. Now pick another value in between pi thirds and 5 thirds pi. How about 1/2? That certainly would work. So f prime of pi halves, I think, is what I heard you say, wasn't it? Okay, I thought so. Okay, and this would be what? 1/2 minus what? Cosine of pi halves. What is the cosine of pi halves? Oh yeah, that's right, isn't it? It's 0. Okay. And what is this? That's positive. We even know the value, 1/2, but that's greater than 0. What does that tell you about pi thirds? It's less than pi thirds coming in, and it's greater, less than, it's a negative value, the slope is a negative value coming in, a positive value going out, relative minimum. So pi thirds, this one, relative minimum. Okay? All right. What other thing do we need to determine? Okay. We know what it is at 5 pi thirds. Ooh, look at that. Y'all let me write that wrong. Okay, I corrected it before you caught me. Okay. I ought to give points for catching me, but I don't have that many points to give away. Okay. All right. So what do we need next? Some value between 5 pi thirds and 2 pi. What would be a good one? Anyone will do that works. Anybody? Second? Okay, that certainly will work. Y'all are clever to use the pi fourths. I would have been tempted to use the pi sixths that were in between, but y'all are okay. In fact, better off doing this one. Well, I think. Let me see. All right, and this would be what? F prime, remember, was this thing up here. So it would be 1/2 minus the cosine of 7 pi fourths. What was that? That's root 2 over 2 again. Just like we did before, and we know just like before that has to be less than 0. So if coming into 5 pi thirds, your first derivative is positive, and leaving 5 pi thirds is negative, what does that tell you? Relative maximum at 5 pi thirds. All right, good deal. Okay. Now, that's using the first derivative test. What Dawson was saying would certainly work too. Determine the value at your critical numbers, x equal pi thirds and 5 pi thirds. Find out what those values are. Then do the function values at each of the intervals and see whether it's greater or less. Okay, that would certainly work. It's a little more work. Okay. Using first derivative test, you don't care what it is at the value. You only want to know what the first derivative is, left, right, left, middle, and right. And once you know that, you'll know. You won't know the value there, but you'll know that they are relative mins and max. All right, does that make sense? This was example 2. I'm not even on the right page here. Okay. Yep, this is it. So let's see how they did it, if they did it any differently. Okay. Note the f is continuous on the interval 0 to 2 pi. In fact, it's continuous everywhere because linear functions are continuous everywhere. Sine functions are continuous everywhere. The sum and the difference would be continuous everywhere. Okay? And then take its derivative, which is a great idea, just like we did, and determine the critical numbers of this, set that equal to 0, which we did, and that we found out to be cosine x equal pi halves, and that was true at pi thirds and 5 pi thirds. 1/3 pi up from 0 and 1/3 pi before you got around to 0 again. Negative in the other 2 quadrants, you don't care for those. Because there are no points for which f prime does not exist, that was defined everywhere, you can conclude those are your only 2 critical numbers. Okay, so what they did, they liked the tables, and we sort of did it, you know. We picked a value between 0 and pi thirds. This was the minimum value of the interval in question, and this was our first critical value, or number, and this was the first to second critical numbers. And between the second and the end of the interval in question, those are our 3 intervals. Picking one, and y'all must have looked in the book, okay? Y'all pick pi fourths and 7 pi fourths and pi. I would have probably gone for pi 2. Y'all picked pi halves. It works, okay? So you weren't looking at the book for it, okay? So f prime at pi fourths we found was negative because at here cosine is root 2 over 2. 1/2 minus that is negative, so it's decreasing to the left. And then they picked pi, and cosine of pi is -1, okay? And 1/2 minus a -1 would be 1/2 plus 1, which is positive, okay? So that would be increasing to the right, decreasing to the left, increasing to the right, has to be a relative minimum. I haven't written that yet. And then increasing to the left is the second critical point, but decreasing to the right because picking that point, just like we got a negative number at pi fourths, at 7/4 pi. So that meant at 5/3. That must be a maximum. Okay. So, relative minimum at 5/3, and relative maximum at 5/3 pi. Okay. Now, so, make sense? Any questions? Strictly monotonically decreasing here, increasing here, decreasing there. Minimum. Any questions? That was example 2. Oh! They skipped 3 and 4. So let's go back and do example 3. Find the relative extrema of f of x. I do have my watch. Okay. Okay. Equal. Ooh, nice one, huh? They do the easy ones and leave the others without, not on the PowerPoints. X squared minus 4 raised to the 2/3 power. Find the relative extrema of that. How would you proceed? Take a derivative. I knew he was going to say that. Okay. F prime of x would then be what? 2/3 x squared minus 4 to the negative 1/3 times 2x. Okay. Now, if I can write that slightly differently, okay, here in the numerator we have a 2 and a 2x, so that'll be a 4x in the numerator. In the denominator we have a 3, and then we have a cube root, that's what the 1/3 is, the minus puts it in the denominator, of x squared minus 4. Okay. Find the relative extrema of that. And by the way, oh, I'm sorry, I'm looking at the wrong problem. Okay. Yeah. I had it right. Okay. Now, they kept it as a thing I just sort of prefer. In this case, doing the calculations, it might work a little better. Doesn't really matter. Now, what's the next thing we need to find? Second?
Critical values.
Critical values, and what would they be?
If you set it equal to 0, it wants me to set the denominator equal to 0.
Okay. Okay. I missed the first part of what you said, but if you said it this way, it's a pretty clever way of saying it. Anything that makes the numerator equal 0, that's going to make the first derivative 0. Or anything that makes the denominator equal 0, that means not defined. Okay? So those are 2. There is one other. Oh, not for cube roots, though, is it? If that was a square root, then what's inside there could not be negative. But a cube root, we can. So that's all we're interested in. What makes the numerator 0 or what's makes the denominator 0. Those are going to be our critical values. Notice they didn't give us a given interval. So we're assuming what? All real numbers. So, what value would make that numerator 0? Yeah, x equals 0. X equals 0, critical value, okay, or a critical number. Okay, that's the only one. How about that denominator? What would make that 0? X equal 2. Is that all? Negative 2 would work too, wouldn't it? Because that would make your radical, what's inside the radical 0, cube root of 0 is 0, 3 times 0 is 0, can't happen. And those are the only 2 that would make that the case. So, even though, they didn't explicitly tell you this, but this is a function that's good for any value. Okay, you can take the cube root of any positive or negative, whatever, even of 0. That's okay. Once it gives a denominator, it's not okay to be 0, and that's the only values. So here we have our 3 critical values. Okay, so what do we do next? Second? Okay, we determine our 3 intervals. What will they be? Okay, 0 to 3. Wait, say it again. 0 to 2 is that what I heard? Oh, wait, we got -2 to 0. Anything else? Where does all real numbers? Oh, negative infinity up to -2. -2 to 0. 0 to 2. And 2 to positive infinity. Okay. Now, we could calculate values in there of the function, or, a little bit simpler, calculate values of your first derivative. So, you need to pick a point between negative infinity and -2. Keep it easy, because we're going to be trying to do our first derivative there. Second? -3. Let's try -3. Okay, and we're interested in f prime at -3. The other way, f of -3, we could do that too, but we're going to do f prime at -3. Okay, the numerator is -12. Okay, the denominator is, okay, at -3, this is going to be 9 minus 4, right? Which is positive. Cube root of a positive number is positive. 3 times a positive number is positive. So this is the first derivative of f prime of -3 is less than 0 because the numerator is negative. Okay? Pick me a point between -2 and 0. -1. Okay? Now let's do our first derivative at -1. Okay? Alright. At -1, what's the numerator going to be? -4. Okay, it doesn't matter what value, it's going to be negative. And the denominator? Yeah, because inside will be a -3, cube root of a -3. I don't know what it is, but I know it's negative. Okay, and 3 times a negative, so that's negative. So this is going to be negative divided by negative is positive. Okay, so your first derivative, f prime of -1, is greater than 0. So what do we know we have here? At second minimum. Okay, so f at -2 minimum. Okay. All right. Let's go on to 0 to 2. What's the numerator going to be? Oh, wait, pick a point. 1. I like it. Okay. And then what's your numerator going to be? Positive. The denominator, though? Negative. So positive over negative is negative. So that means that f prime of 1 is less than, I can't write, less than 0. Negative. Okay. So f prime to the right of negative. The right of 0 is, look at the right. To the right of 0, the first derivative is increasing. To the left of 0 is decreasing, what does it make it at 0? So to the left it was increasing, to the right it's decreasing. That's a max. Okay. All right, let's go to 2 to infinity. Give me a value. Second? 3, I like it. Okay. And what's the numerator there? Positive. Okay, what's the denominator? Positive. What's your first derivative? Greater than 0, positive. So it's negative to the left of 0, to the left of 2. It's positive to the right of 2. What does that tell you? Min. Relative minimum. I really should be putting relative in there because they're not absolute, but it's just easier writing them. Okay. So does that make sense? Okay. We don't know the values of any of these places. We could figure them out, sure. But all we're interested in, I think, it says find the relative extrema. No, really, we do care what the value is, because to find the extrema, you really need to give ordered pairs, right? I haven't been doing that. Sorry about that. We need to give ordered pairs, okay? So we need to go back to your here. We know here at negative 2, f of negative 2 would then be, that's going to be pretty easy to do, isn't it? F of negative 2. There's your F. F of negative 2 is not that hard. Put a negative 2 in it, x and square it.
0.
It's 0. Good. Okay. So this is going to be a relative min. I'll put relative this time. Our next value was 0. Alpha of 0. What is that value? I can't hear it. I heard something, but I can't make it out. Okay, plug in a 0 there. What do we have? Negative 4 squared is 16, so that'll be the cube root of 16. Okay, whatever that is. Cube root of 16. You said about 3.5? 2.5, about 2.5. Okay, and we know that's our relative max. That sort of makes sense. It's greater than the other one, so it makes sense for that to be at least a relative max. And at our third critical value, alpha of 2, what is the value there? Plug it in here. You're what? 0 again. And we know that's a relative min. So to answer the question, it said, find the relative extrema. The extrema are points. You need x, y values. So it's negative 2, 0, 0, root 16, and 2, 0. Okay? Those are the 3 points, and we know what they are. Relative min, relative max, and relative min. So we do need to calculate those. So actually, Dawson's method of doing the other way would work just as well. Okay? Because you had to do it anyway. Okay. Good deal. And we didn't draw the picture. If you want to see the graph, look in the book, okay? And it's there. Okay. So decreasing here, reach the minimum there, increasing after it, reach the maximum there because it's decreasing after that, first root is negative. And then reach the minimum there, and first root is positive after that. So a fancy looking W or something like that. Now, notice your function was continuous. Your first derivative is not continuous, but we don't care about that. The first derivative, all we are interested in is increasing or decreasing on either side. The non-continuous or not defined values, that gives us a critical number just as well as the other. So that was example 3. Okay. Okay. Another little warning here before we go to example 4. When using the first derivative test, be sure to consider the domain of the function. Okay? And I think I'll erase this so I can actually write down what they're talking about here, because I know not all of you have your books with you today. You may have them on your computers, but there it is. Here's your function. This is not an example, it's just before the next example. Oh, it is the next example after all, isn't it? So this is example 4. F of x is equal to x to the 4th plus 1 over x squared. Okay. Now we can proceed along our merry way, if your way is merry, but what's a potential problem here? And whenever you have a function like this, it's a good idea to note the domain. Why this problem? What would be the issue here? Yeah, you could have a 0 in the denominator. You can't have a negative in the denominator. That's never negative. But who cares about that? You could have a 0 there. So if that was a square root, yeah, well, so anyway, you would look at all the things. So here we know x cannot equal 0. Identify that right off the top. X can't equal 0. So don't mess with anything at 0. That may give us an extra, and it will, interval that you have to worry with. Because you can't have x equals 0. So anything to the left of x has to be considered separately from anything to the right of x, because it can't equal 0. Okay. Bunk. Now, it says find the relative extrema of this problem. What would be the, after you identify your domain, then what would you do next? Take a derivative, f prime of x, and this. Now, how would you proceed with this? Quotient rule. I was afraid you were going to say that. Here's what I would do. If I can avoid the quotient rule, I usually do. I would rewrite this as what? Maybe x to the 4th over x squared plus 1 over x squared. Was that legal in most states? Okay. The first term would be x squared. Second term would be plus x to the minus 2. I'll even see a quotient now because I've hidden it. Okay. Now, I would take a derivative of that. What would that be? 2x minus 2x to the negative 3. Perfect. Okay. All right. Now that you've done your, and now rewrite that back like this. 2x minus 2 over x cubed. Okay. Now, what would you do next? I don't care what I'd do next. What would you do next? Taking your derivative, set it equal to 0. Now, we need to do some solving here, don't we? How are we going to do that? Help me, somebody. Okay, that would certainly work, and that would give us I'll multiply everything on both sides by x cubed. What does that give us? Say again? 2x to the fourth on the left, that's the first term. Second, minus 2 is equal to, I'll do the right hand side, 0. Okay. So I didn't want you to have to worry with that one. Okay. Next. Second? Okay. I did it. Okay. That would be x to the fourth minus 1 equals 0. I divided both sides by 2. Okay. That's legal in every state. Now what? You could. Usually a safer bet would be to, what's the F word? Factor. And what would that be? X squared plus 1. Are you through factoring? Yeah or nay? No. Keep going. X squared plus 1, will that factor? No. No. X squared plus 1 never will factor. Sum of two perfect squares never will factor. But how about the difference of two squares? What would that be? Okay. Now, what zeros do you get here? X equal -1 and x equal 1. Now, in the first rendition of our first derivative here, what other thing do you see is not equal? I mean, critical value. X cannot equal 0 again. Down here you mask it because you multiply both sides by x cubed. So don't count on this. Look at up here, okay? Rewritten like this, then you see x cannot equal 0. Down here you don't see x can't equal 0. Why? How did you get rid of that problem, child? When you multiply both sides of the equation by x cubed, what if x was 0? You're multiplying both sides by 0, and then you got 0 equals 0. Perfectly fine, right? You just wiped out all possible values. So it wasn't good to multiply everything by 0, so therefore, at that step, you should have said x can't equal 0, because you don't want to wipe out everything. Okay? So we also have x cannot equal 0, but we had that up here too, right? So there are our three critical values, you might say. It gives us that interval there. If you just counted on this down here, you might miss it. Look at the original rendition of your first derivative.
What about for the x squared plus 1, x squared can equal -1?
Okay. Oh, the x squared can't be -1. You're absolutely right. I agree. X squared cannot equal -1. When is that true? Everywhere in the real number system. You can't have a square equal a negative number. So, sure enough, we'd have some complex zeros, but we're not dealing with those right now. We're only dealing in the real number system. Okay? At that point, yeah, no, not going to happen. Okay. So, these are our three critical numbers. Okay? -1, 0. So, what do we do? And again, they didn't give us, and by the way, this is one of these examples that says see larsoncalculus.com for an interactive version of this type of example. You might want to look at that. So what do we do next? Intervals, and what would they be? 2, -1. Okay. Okay. Now let's pick a value in each interval. Second, -2. I like it. And what we're interested in is f prime at -2. And what would that be? I think this will be the easiest one to do that rendition. It'll be a -4 plus 2/8, which would be -4 plus 1/4. Who cares what it is? It's negative, right? Okay, so this is less than 0. Okay? Pick a value in that next interval. -1/2. Oh, I should have done it up here. And then we'll do f of -1/2. Okay. And again, we'll use this one. F of -1/2 here would be a -1, right? Minus, plus, when you cube a -1/2 becomes a positive 1/8, but that's in the denominator, so you would invert and multiply. What's that? Yes, it is. But I use that negative to change the sign. Yeah, okay. So it becomes 2/1/8, which would be 2 times 8, which is 16. -1 plus 16 is fairly positive. Okay. That's all we're interested in here. Okay. Now, how about what's the number between 0 and 1? 1/2. And f of 1/2 would be, well, this would be 1. And then this would be a minus 16, wouldn't it? No, yeah. Okay. And 1 minus 16, I think, is pretty negative. Okay. And then pick a number between 1 and infinity. 2. And f of 2. Let's go up here to it. That'd be 4 minus a small number is going to be positive. Right? Now, what about f of 1? What is the value there? F of 1. Pretty easy, isn't it?
Are you plugging into the derivative or the original function?
Second?
You plug in f of 1
Into the function. Yeah. What's that? F of 1 is... Oh, wait. I'm supposed to be doing f of -1. I'm sorry. F of -1 would be... Same thing. 2. Okay. Do we plug in f of 0? Is that the next one of interest here? No. That's not, it may have been a critical value, but it's not even defined. We had to use that as an interval, but it's not defined. So we don't do that one. The only other one is f of 1. And what can we say about that? It's also equal to 2. Okay? But we did need to know in between here, so at the point -1, 2, which is our critical value, to the left of that where the first derivative is negative, and to the right of it is positive. So what do we have? Minimum. A relative minimum. Okay? Now, f at 1, see, this we evaluate, we use as a interval setter, but we don't use it as a critical. It is a critical number, but we can't use it as a value because it's not defined there. Okay? So let's do the next one. f of 2, this f of 1 is 2. To the left of 2, you're negative, and to the right of 2, you're positive. So guess what? Another relative minimum, isn't it? Okay. How can you have two relative minimum? Because in between, they could be doing anything not defined up there. Okay. And sure enough, this is how it looks. Okay. It's a curve over here and a curve over there, never define a vertical asymptote at x equals 0. So you don't expect to be a value. It's no, turned out looking like it was a critical value, but it's not. It's the place where the function is not defined. But you still use it as a definer of an interval because you don't want to say, oh, but it's not defined there, so we won't do it. And then if you just use this value and that value and pick some number in between, you may find a wrong answer there. So you have to use the other as a definer of an interval, but it's not a critical number. Looks like it is, but it's not. But it still defines the interval. Okay. Okay. Good deal. Any questions on that? They do have another little technology feature at the bottom that is an interesting step. I'm going to let you do that because I don't have a graphing calculator here to do that kind of stuff. But you'll find it's a pretty bizarre little number there that's given off. And not only did they skip 3 and 4, they also skipped example 5. So let's see. I don't think we're going to have time for example 5, are we? Aren't we almost out? Huh? Oh, we got time. I forgot. I teach 2 4-hour courses. One ends at 20 and one ends at 40. This is the 41. Yeah, we got time to do 5. Let's do it. Y'all were almost out of here, weren't you? Okay. Glad y'all caught me. Okay. All right. Let's do example 5. Neglecting air resistance, the path of a projectile, which in this picture indicates it's probably a basketball in this case, that is propelled at an angle theta, is given by this good old physics formula. Y is equal to minus g secant squared theta divided by, goodness gracious, 2v squared, v naught squared. All that is times x squared plus, I can't read, is that tangent theta? Yeah. Times x plus h. All right. Now this is good for 0 less than or equal to, strange but true, theta less than or equal to pi halves. Now, this guy's shooting a basketball, but a projectile could be a rocket you're shooting or a weapon of some nature too. And let me just say this. Never shoot a basketball. Not even dunking would you shoot it straight up. You shoot it straight down then because you're dunking downward, okay? Don't throw a basketball straight up. I don't think you have much a chance for it going in the hoop unless it goes in and then comes back down, which doesn't count either, okay? So I don't know why they allowed you to equal pi halves. And equaling 0 is not going to be a very good shot either. Basketball, if I shoot it that way, again, unless I'm dunking it, which it's never going to happen. You know, that doesn't make a lot of sense either. But it's okay to have them there. That defines the problem. It's okay. All right. Now, remember, by the way, what is G? Second? It's the acceleration due to gravity, which is a constant everywhere on the surface of the Earth. So don't be shooting basketballs anywhere other than the surface of the Earth, okay? Okay? And theta is, you're given, that's the angle at which you're shooting between 0 and pi halves, but never at 0, never at pi halves either. V0, that's your initial velocity of the ball. Once it leaves your hand, that's what it is, and that doesn't change. So tangent theta. So all this is a constant. And this is a constant. And that's a constant. H is your initial height. Now this guy looks like he has a pretty good jump there, and he's releasing it from somewhere about here. Now let's just say he's 6 feet, just to give a height to it. So I'd say his initial height there is probably pretty close to 7 feet. Just making a guess. Okay?
So it says the height is 9 feet.
What's that?
I think the height is 9 feet.
Oh, 9 feet. Goodness gracious. He's either tall or he's got a really good vertical leap there. Okay. Yeah. Okay. So initial height is 9 feet. So he could be shooting this almost straight, but not. It still wouldn't get there. Okay. This equation derived from, okay, if you want to go to section 12.3, you can go there. The G is 32 feet per second, which is the acceleration due to gravity in the U.S. customary system. V0 is 24 feet per second. That's his initial velocity with which he's shooting. And H equals 9 feet. I see it now. What value theta will produce the maximum horizontal distance? What's the horizontal distance? By the way, I left off this. Y is the height, not H, but the height, and X is the horizontal distance. So Y is the vertical distance at any moment, and X is the horizontal distance at any moment. Okay? For what value of theta will produce the maximum horizontal distance? I think I can answer this already. No, maybe not. Okay. All right. Now, theta is a constant. We just don't know what it is. G is a constant. We do know what it is. So let's fill in what we do know. So this Y is equal to minus 32 secant squared theta, we don't know what that is, divided by 2 times, so what did I say, 24, so that would be 48. Ooh, no. 24 squared times 2. Someone do that on a calculator for me somewhere. 24 squared times 2. Say again? A little louder. 1152. One of my favorite numbers. Okay. All right. X squared plus, we don't know tangent theta either, X plus, didn't we say that was 9? Okay. There's what your Y is. Where theta is a constant, we just don't know what it is now. So how are we going to get the maximum horizontal distance? Is that right? Okay. Let's first divide 32 into 1152 and see what we get. Second? 36, you said? Yeah. Yeah, 1 over 36. Okay, got it. That's what the book got to. Okay, good. So let's rewrite this. This is equal to minus 1 over 36. Let me just put secant squared theta over 36 x squared plus tangent theta x plus 9. All right, there's your y. Use the maximum horizontal distance. Okay. Here's the problem. Okay. You don't take a derivative of this. That would give you the maximum y, and that's not what they asked. That's why I kept reading the problem. Are you sure this is what you're asking? So what they're doing here is having to solve this quadratic equation for x. And that's taking the quadratic formula. Ew. Okay. What they say let y equals 0. Well, why y equals 0? Maximum horizontal distance. Okay, is shooting a basketball, as long as you're going something between or anything like this, the y is never negative, right? You're some angle between 0 and pi half, so you're shooting it up. So it's never negative, so where it hits the ground, that's going to be the maximum horizontal distance. So that's why they set y equals 0, okay? Then you can use your quadratic formula to solve that really outstanding looking equation. Negative 1 over 30, or this one right here, I'm not going to write it again, okay? We just set this equal to 0. I just don't have much room. Set that equal to 0. And then you do the quadratic formula. Anyone remember it? X is equal to how does that go? Not yet. Minus b, so minus tangent theta, that's your b, plus or minus the square root of what was that part? B squared, so that would be tangent squared theta, minus 4 a here, goodness, it's a plus, it's a minus 2, so that's going to be plus 4a, which is secant squared theta, over 36, c, which is 9, so make that a 36. Oh, clever, wasn't it? Okay. All right. Over 2a, which is minus secant squared theta over 18. All right, clever, I said, because the 36 and the 36 is cancel out there, and you wind up with the square root of tangent squared theta plus secant squared theta, if I did it right, okay? Now, that's not a trig identity, I know. I know that tangent squared theta plus 1 is equal to secant squared theta. Y'all knew that too, right? Please say yes. Okay. You better know it. You were in my trig class, okay? The rest of you get by okay. Remember that one? So here we have a tangent squared theta plus a tangent squared theta plus 1. So this could be written, just that radical is the square root of 2 tangent squared theta plus 1. Not that that helps us any, but, well, maybe it does a little bit.
How did the 36 cancel out?
Because you had 36 in the numerator and 36 in the denominator, didn't you?
I thought it was a 4.
The 4, okay, the 4, a was secant squared theta over 36 with a minus sign. That made that's a plus there. And you had a 4 in front of it. But then you, c is 9. 4 times 9 is 36. Yeah, over 36. That's why I said it was just clever how they made that happen. But I'm wondering if we want it the other way. I don't know. It's a pain in the neck or some other body part. And wow. Don't they do wondrous things here with their trig functions? They left the tangent squared plus secant squared in there for a little bit. Okay, so how are we doing on time? I think we're going to run out of time before we run out of problem here. They didn't change that, so I guess I'll go back and not change it either. But you see, they did wind up with that same radical. So let me do some erasing at the top here, so because I have no room to write. Let me erase this and this, okay, and put it up here. So what we have here is x equal to, now, they're going to change everything to sines and cosines, which is not a bad idea. So it's minus sine theta over cosine theta, okay, plus or minus, and I think we can get away with saying, let's just deal with the plus one, okay, because when you do a minus, you have negative, and you don't want the maximum distance to be behind you. Okay, so we're just going to use the plus. So let's just use the plus here. Oh, take that back. You have a minus down here too. So let's just forget the plus and change all these minuses to plus. Okay, so that'll be a plus sine over cosine plus the square root of, and tangent squared plus secant squared, that would be sine squared theta over cosine squared theta plus 1 over cosine squared theta. That's all under the radical. Divided by 1 over 18 cosine squared theta, which is then multiply, or do 1 over or 1 over, that would be multiplying. So what this comes out being is 18, from that being pulled up to the top. You have a cosine squared theta now on top and a cosine on the bottom, so this would be a sine theta cosine theta plus, now here we have, you can pull out the cosine theta, it's going to cancel one of those out, and you have a sine squared theta plus 1, which is a real pain in the neck too. And then you also have that other cosine theta here too. Now, I know it's really...
What is that? You said that's 18 times square root of...
Okay. Okay. The 18 came from here when you flip this over, because this is 1 over this, because it was already there. So the cosine squared theta went up top. It will cancel this one out, and when you do least common denominator, it'll be square root of cosine squared, which is cosine. So you have a cosine here too. So you have an 18, and you could just factor that out. 18 times sine theta cosine theta plus, pull out the 18, and probably pull out the cosine theta too. And this would just be square root of 1, square root of this thing. Okay. So let's see if doing all these pulling outs will do any good here. I don't know where to, wrong thing. Okay, we're running out of time. I think we're completely out of time now, but let's go on and get rid of this. That was no good at all. Okay. Let's give what this answer is here, and I'll leave the rest for the student. That's what instructors usually do, isn't it? 18 cosine theta, that's in both of those, times sine theta plus the square root of sine squared theta plus 1. Okay. And that's what your x is equal to. That's what you're wanting to take a derivative of. Now, oh, by the way, these x's now have to be greater than 0. That's why we threw away the other one. So, that's what you take a derivative of. And that looks like a lot of fun. I wish we had time to do it. That would just be delightful to do in the next 7 hours we would have together. But we just don't have time to do it. So you have to do that. Take the derivative of that. It looks like a wonderful product rule. And the second part of the product rule has a fantastic chain rule in it. And you go from there. You set that equal to 0 and find your critical point. And I think you'll come up with an answer. Okay? At this point, you need to find the value, blah, blah, blah. Applying the first derivative test by hand would be very tedious. Using technology, do it. That's where we stop. Okay? So, anyway, they stop too. Okay? So, we're not going to do it anymore. Let me give you homework exercises here, 3.3. Do number 3. It's at calcchat.com. Any of the odds 5 through 9, they're all at CalcChat. 5's at CalcView. Any of the odds 11 through 17, they're all at CalcChat. 13's at CalcView. Any of the odds 19 to 39, all at CalcChat. 21's at CalcView. Any of the odds 41 to 47, they're all at CalcChat. 41's at CalcView. Any of the odds 49 to 53, they're all at CalcChat. 55's at CalcChat. Any of the odds 57 to 61, they're at CalcChat. Now, the exploring the concepts, you don't have to do these. If you want to play with them, go knock yourself out. Either 63 or 65, should be at CalcChat, and either 67 or 69, they should be at CalcChat. 71 should be at CalcChat. 73 should be at CalcChat. Okay, I'd say then choose any of the ones 75 through, 79. They should all be at CalcChat. 81 or 83 should be at CalcChat. 85 should be at CalcChat. 87 or 89 should be at CalcChat. Then there's some true false, 91 through 95, they should be at CalcChat. And then there's a couple proofs if you want to do those, 97 and or 99. Wow. Okay. We'll pick up next time 3.4. Good deal. This is one long chapter, by the way. Very long chapter. Okay. Do you want me to record this or not? No, it's up to you. I mean, you're not in the way, but just do you want me to record this? Okay, yeah, go ahead.
Okay, so I got lost right here. Okay. So, you said divide out the sign and you made all these positives.
Right.
So what was there was a negative tangent.
And this was a negative down here too.
Oh, the negative secant. Okay.
Yeah.
So you just divided this negative and this negative.
Yeah. And then throw away the positive up there so that all becomes positive.
Okay. And then right here, this is where I was confused.
Yeah. Oh, mine was ugly on the board too. That square root covers the denominators.
Okay. So when you got to this point, that's what I was asking about right here.
Yeah.
So the cosine is the cosine of
Theta is just ugly.
Is it under here?
Or no, it's outside.
So
here's what I was doing. You see,
it's right here.
Yeah. Okay. Right. Yeah. You see this down here? Flip it over and multiply it through right there.
Oh, the whole thing.
Yes, exactly.
So my 18.
So that's where the one cosine went here, because you had a cosine theta cosine squared theta on top. 18's on top, cosine squared theta is on top, and it wiped out this cosine.
Oh, so this is a cosine squared theta right here times this.
Yes, exactly.
And that's my 18 cosine squared theta. And over here, it wiped out.
Only this is just a cosine too, because the square root of cosine squared is cosine in the denominator, so that's just a cosine there.
Okay.
It's 2.
Test 2. Okay.
Okay. All right. Thank you.
All right, is that all you needed?
I think so.
Okay, great.
And this is right. The bottom. This one is left.
Yes. What's that?
This is what was left. 18 cosine theta times sine theta plus sine squared theta plus 1 all on the numerator.
Yeah.
And this is what you said, take the derivative of and then get the points.
Yeah. It looks like a lot of fun. And then at some point they say, and after this it gets complicated, so do it or do it, whatever they say there. I thought it was getting complicated well before that. Okay.
You go to for me real quick.
What's this again?
It's progress report for STEM.
Oh. Do I have to put how badly you're doing? We only turned in one thing, so. Contributed to class discussions and activities. You're awfully quiet back there on behavior. Goodness gracious. Okay. Whoops, you have to sign this, not me. Okay. That's unusual. I would have thought I had to sign it. You could have filled it out, huh? Okay. I'm just kidding. Okay.
Is there a like a library on this campus or something?
Yeah.
Where's it?
Okay, let me get this shut down first.